Today, we will talk about the vertical speed indicator. This is one of the basic flight instruments that we will find in any aircraft. And its operation depends on the air pressure information provided by the pitted static system. Here we have a typical pitted static system schematic. As we can see, the vertical speed indicator is connected only to the static port, which means that it receives static pressure information only. Now, the vertical speed indicator is abbreviated as VSI, and sometimes it is referred to as the variometer. This is an instrument that measures changes in altitude. In other words, it indicates the rate at which the aircraft climbs or descends. So looking at this instrument, the pilot can tell if the aircraft is in level flight, climbing, or descending, and how fast is the altitude changing. Usually, this rate of climb or descent is expressed in feet per minute. So, let's now see how to read the instrument. The VSI can be divided into upper and lower parts. If the needle is in the upper part, it represents a rate of climb. While if it is in the lower part, it represents a rate of descent. In this particular case, each of the instrument's markings represents 100 feet. In this example, the needle is pointing 0. Therefore, it indicates that the aircraft is in level flight at a constant altitude. Now, if the needle moves up like this, it would be indicating a rate of climb of 300 feet per minute. On the other hand, if the needle moves down like this, it would be indicating a rate of descent of 500 feet per minute. In this other position, it would be indicating a 800 feet per minute descent. And here, it would indicate a 1000 feet per minute climb. Again, in this instrument, the scale is expressed in hundreds of feet, however it may vary depending on the instrument design. Now that we know how to read the instrument, let's see how it actually works. The vertical speed indicator measures changes in atmospheric or static pressure to give its reading. It takes advantage of the fact that the static pressure decreases with altitude. So at lower altitudes there is a higher pressure, while at higher altitudes there is a lower pressure. With this in mind, we could say that if there are not static pressure changes, it means that the aircraft is in level flight, and therefore the VSI will indicate 0 feet per minute. On the other hand, if the aircraft starts climbing, the pressure will gradually reduce, and therefore the instrument will interpret it as an altitude increase. Now, once the aircraft stops climbing and maintains level flight again, the pressure will remain constant, and the instrument will return to indicate 0 feet per minute. Conversely, if the aircraft starts descending, the static pressure will gradually increase. So the instrument will interpret this as an altitude decrease, indicating the corresponding descent rate. And once again, when the aircraft levels off, the pressure will remain constant, and the VSI will return to 0 feet per minute. In general terms then, the VSI interprets changes in pressure as changes in altitude. And measuring how fast the pressure is changing is how it can determine the rate of climb or descent. That's why it is necessary that the instrument receives static pressure information from the static port. So far, we have seen the basic principle of operation, but let's see more in detail. How does the VSI actually measures the changes in static pressure? Well, the static port is directly connected to an elastic capsule inside the instrument case, which in turn is connected to gears that move the needle in the dial. Now, a second static line is connected to the instrument case, however it incorporates a calibrated leak, which causes the pressure changes in the instrument case to be more gradual. This way, it is possible to measure how fast the static pressure is changing. Let's see how by means of this example. First, let's look at the level flight situation. In this case, the pressure inside the instrument case and the pressure inside the capsule are equal. Therefore, the needle will point 0 feet per minute. The situation changes if the aircraft starts climbing or descending. Let's look at the descent scenario first. In this case, the static pressure will increase in the capsule almost immediately. However, inside the case, the pressure doesn't increase that fast due to the calibrated leak which restricts the flow to the case. This way, a temporary pressure difference is created between the capsule and the case, causing the capsule to expand and move the gears to indicate a rate of descent. Let's now see the climb scenario. In this case, the static pressure will decrease almost immediately in the capsule. However, due to the calibrated leak, it doesn't decrease that fast in the instrument case. This creates a pressure differential which causes the capsule to contract, moving the needle to indicate a rate of climb. Now, this instrument isn't perfect. Just like the altimeter, the VSI suffers from instrument error, which is caused due to mechanical imperfections and wear of the gears. And it also experiences position errors due to inaccuracies of the pitted static system while measuring the static pressure caused by maneuvers and changes in aircraft configuration. However, these are not the only errors present in this instrument. There is another one known as the lag error. This is basically a delay in the instrument indication due to rapid changes in climb or descent rate. This happens because the capsule doesn't have enough time to contract or expand rapidly. Usually the delay varies between 1 and 4 seconds. It happens, for example, when the aircraft is in a constant descent and it suddenly levels off. In this case, it will take a few seconds for the VSI to indicate a level flight. This can also happen when the aircraft is in level flight and it suddenly starts a climb. Again, it will take a few seconds for the VSI to indicate the corresponding rate of climb. Now, this type of error can be counteracted using an IVSI. This stands for Instantaneous Vertical Speed Indicator. Basically, it is a regular VSI that incorporates a vertical acceleration pump to compensate for lag error. This vertical acceleration pump consists of a piston inside a cylinder. This way, the inertia moves the piston inside the acceleration pump up or down, inducing an instantaneous movement of the needle. Let's see an example. Suppose the aircraft is in level flight and starts a sudden climb. In this case, the inertia causes the piston to go down, which in turn produces kind of a suction, causing the pressure in the capsule to reduce rapidly. This has the effect of an instantaneous climb rate indication. Obviously, this situation is temporary, since the springs inside the acceleration pump will return the piston to the neutral position. And then the instrument will work as a regular VSI. Now, in case of a sudden descent, the inertia will cause the piston to move upwards in the acceleration pump. This causes a rapid increase in pressure inside the capsule, which has the effect of an instantaneous descent rate indication. Again, the springs will return the piston to the neutral position, and the instrument will continue to work normally. However, a problem related with this design is that it may give erratic or erroneous indications during steep turns or maneuvers, or in turbulent conditions. While flying in turbulence, this happens because the piston moves constantly up and down, causing the needle to move erratically. On the other hand, when executing a steep turn, the piston will be held down by the load factor, causing the instrument to artificially indicate a climb. That's why in most modern aircrafts, the vertical speed indication is augmented by the inertial reference systems, which counteract this error. Now, you might be wondering by now, what happens with this instrument in case of a static port blockage? Well, in this case the VSI reading will gradually return to 0 feet per minute. And it will remain still indicating level flight. This happens because the pressure in the capsule and inside the case is the same, and since there's no pressure differential, the instrument will interpret it as a level flight. So, how can we solve this situation? Well, most aircraft incorporate an alternate static source, which must be activated in case a static port blockage is suspected. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe and leave a comment down below. Thanks for watching.